Okay, so we last left off with the interfacial energy. We had the interfacial energy squared, and the composition profile that you need to plug into that is a solution to this equation here, equals 0. So the question here is how do we in order to solve this equation here, the Euler-Lagrange equation, you need to commit to a certain free energy function. And then once you solve this equation, you have to be able to plug it back into here, dx, in order to get the interfacial energy. And in order to be able to do this analytically, we want to look for an analytical solution. And that implies you can't use the regular solution. Regular solution model that we started with the logs, C1, C log 1, C1, C log 1, all that kind of stuff. And so what we're going to do is you're going to use a polynomial and these are sometimes called Landau expansions. Polynomial approximation of the free energy. And so we're going to couch this in terms of an order parameter, phi, and the free energy is a function of phi, looks like this. And the equilibrium phases are given by 0 and 1. And so you just basically define an order parameter, if you want to think about it in terms of what we've been talking about before. That looks like that. So it goes from 0 to 1 as you go from one of the equilibrium phases to another. And the particular free energy function that we're going to use is some constant A. So A is an energy per unit volume. And it sets the energy scale here. So a couple of words about this free energy function. This is a polynomial expansion. It doesn't have any of the logs in it, right? And so that means that this polynomial free energy doesn't do very well, or it's meaningless once you get outside 0 and 1. But since we're only going to be going from one equilibrium phase to another, this works perfectly well because we're not going to be worrying about what happens, as you go out there. So we're basically going to just go from one phase to another as you go across the interface. There's a certain the height of this free energy is A over 16. If you work this out. And so the important thing is that A basically sets the height of the barrier. The 16 is not important. It's really A. So A sets the height of the barrier between the two phases. And so A basically is a representation of the energy required to go from one phase to another across the interface. It has df d phi equals 0 at phi is equal to 1, 0, and 1/2. So you have equilibrium at those locations. And of course, by equilibrium, this is a half, so this is 1/2 right in here. 1/2, and that means that basically the system is unstable. It's unstable equilibrium because it's going to go one way or another, and we'll talk precisely about that in a second. Okay, and so we're going to rewrite this f of c to an f of the order parameter. So now phi is a function of x, just like the composition. And then you can just put the free energy in, because we have that already. It's A equals 0. And so you can, now you're left with a differential equation for phi as a function of x. So remember, this is the Euler-Lagrange equation, and what we're trying to do is to determine phi as a function of x. So d phi dx is going to be equal to A minus phi. And so if you remember the Euler-Lagrange equation, when we first derived it, had a term that would look like partial f with respect to phi, right? Minus 2k. And by rewriting it in this form that you see over here, you reduce the number of derivatives, and you don't have to take the derivative of f with respect to phi, which is kind of messy. And you can basically integrate this equation in a much more simpler way using the integrated form of the equation. So this is, again, just an ordinary differential equation, but it's separable. Dx, which means you can integrate this, both sides. And the integral of the left-hand side is just 2, the inverse hyperbolic tangent of 1 minus 2 phi. And this is going to be equal to A over k, the 1/2 times x, which is position, plus some constant b after you do the integration. If you wondered how I went from here to here, the answer is I went to Mathematica.
So, you can do this thing. 1 by 5 into 1 minus 5 equal to A by 5 plus B by 1 minus 5. You can find out what those A, B are. So you have to.
Oh, you have separated by factors.
You get exponential, and that will turn out to be.
Yeah. Okay.
I mean, we can give that as a tutorial.
Well, you could just take the derivative of this. Okay. Yes. Okay. So you have a constant here, b. So what's going to set b? And b basically is reflective of where you're going to put the interface. There's a certain it's called translational invariance of this problem about where the interface is located. Because remember, in the back of our minds, we have this interface that looks like this. And where are you going to put this interface? And so let's say we put the interface at 0. So we're going to say phi is equal to 1/2 of x at x equals 0. And so if you plug in phi is equal to 1/2, the inverse hyperbolic tangent of 0 is equals 0. And if x equals 0 is also that location, that implies that b is equal to 0. So you could just eliminate that. And the interface will be located at exactly 1/2. The interface, that 1/2 will be, but you can put it any place you want. This just happens to be convenient because it eliminates this constant b in the problem. And so that means that 1 minus phi is going to be equal to the tangent, the hyperbolic tangent of minus a over k to the 1/2 x over 2. Let's see. Yes, minus, right? And you know that the hyperbolic tangent of minus x is going to be equal to the tangent is minus the tangent. It's an odd function of x. And so that gives you 2 phi minus 1 is going to be equal to the divided by 2. Or phi be 1/2. Whoop. Delta, where delta is equal to k. Yeah, definitely. Sorry. Yeah, I was looking at the definition. Yeah. A to the 1/2. So A is equal to an energy per volume, or length cubed. K is equal to an energy per length. That's the gradient energy coefficient. And so you can see that delta has units of length. So it's a characteristic length of the interface. And this is kind of a key factor here. The tangent of infinity is going to be equal to 1, which implies that phi is equal to 1. And the tangent minus infinity is equal to -1, which implies that phi is equal to 0. And so you have a plot that looks something like this. That looks something like that. It's hyperbolic tangent. That's a bad hyperbolic tangent fig, but gives you an idea. Okay. So all the physics of this problem is basically embedded in that term there. So let's kind of test our understanding here. Delta here is a characteristic width of this interface, and by characteristic, you have to be very careful about this, that it's characteristic, right? So factors of 2, 3. I'm not talking about just the characteristic length, because the actual width can be different from this from a computation standpoint. But just the characteristic width is on the order of delta. And so let's think about our free energy curve. Looks like that. Remember this thing here, that was like A over 16. If the energy required to go from one phase to another gets very, very small, right? That means that there's no energy cost on actually traversing the interface here. So as A goes to 0, delta goes to infinity, which means the interface gets infinitely long, right? By contrast, if K is very large, that means that the system it costs energy to create gradients, and the system tries to minimize the amount of gradients out here, and so you get a very steep profile in the middle. Okay, as K goes to 0. I'm sorry, as K goes to 0, delta goes to 0. Yeah. As K goes to 0, delta goes to 0, which means you get to a very steep interface like this, and that basically means the gradient energy doesn't cost anything. Okay, and so this basically captures the basic dependence of the interfacial and the interfacial energies in the context of this particular free energy function. Okay, so when you're doing a general phase field method, like many of you have been talking about, Cal-Fed free energies and things like that, these relationships don't hold because this assumes this very specific free energy function that's here, it's this one. But you'll still get this kind of same sort of scaling about the relationships between the amplitudes here, the height of the barriers, and the widths of the interface. Okay, questions? Okay, so now that we have this, we can take this equation and put it back into here to determine the interfacial energy. So we know that sigma is going to be equal to 2 times the integral from minus infinity to infinity of k dx. D phi dx is 1/2 1 minus the hyperbolic tangent squared of x over 2 delta times 1 over 2 delta. So that means d phi dx minus x over 2 delta. So we put that back into sigma. Delta squared times dx. And so, which is equal to k over 8 delta squared of the hyperbolic secant to the 4th dx. And again, I never did too well in elementary calculus, so I use MATLAB to do or Mathematica to evaluate this, and this whole thing comes out to it's k over divided by 3. So the important point here is that sigma looks like 1/3, 1/2. So as a goes to 0, sigma goes to 0. So basically, as the amplitude gets very, very small, so as this gets very, very small, the interfacial energy goes to 0. And that's basically because you're going towards a critical point where the difference in energy between the two phases gets smaller and smaller, so it doesn't cost any energy to create an interface. So it gets very, 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 very small. As k goes to 0, the energy goes to 0 too, because you don't have any interfacial gradient energy effects. And so the summary here is quite important, is in terms of phase field models. And delta is equal to k over 8 to the 1/2. And so let me talk about this a little bit now. So if you're trying to model a real system, right, a real system, you can ask the question about whether you ever get a system with a free energy function that looks like this. That's exactly this. That's this polynomial function with a, right? And so what people have done, so it's actually very unusual to have a free energy function like this, and you can ask lots of questions about whether this free energy function, which is a free energy function, actually even exists between the spinodal because of the presence of fluctuations. That's an interesting question from a statistical mechanics standpoint. And so to a certain extent, this parameter a that we put in this, that's present in the regular solution model, is basically a mean field, in some way, a mean field model where you've gotten rid of fluctuations. Otherwise, you can't evaluate a. So the question is where do you get a? And so the way people use this empirically is to say, well, I measure this thing experimentally, and if you do an atom probe experiment, you can measure that thing experimentally by actually measuring the composition profile through the interface, and you have two equations and two unknowns that fixes a and k. And so you can continue then to calculate with the parameterized model. 99% of the time, you never have the atom probe measurement to give you delta. Okay, this is the trick that gets used all the time in phase field models. It said, okay, I really don't want to use an interface thickness that's 10 microns, that's 10 nanometers, because my particles are 10 microns, right? And if you use an interface thickness that's 10 nanometers, you're never going to be able to do the calculation. So let me choose an interface width that's maybe 1 micron. I can do the calculation. It's only 1/10. I can put a lot of grid points in there. I can get a reasonable answer. And I want to make sure I get the right interfacial energy. So I choose this from experiment, and you just pick your A and the K, and you get a well-characterized model with a completely physically unrealistic interface. And the question that you have to ask, and things you have to be very careful of, is what is the effect of choosing an unrealistic interface thickness? And this is one of the major challenges that when you're doing phase field modeling, is to convince yourself that whatever your answers are, they don't depend upon this interface thickness in some unrealistic way. And there are well-known problems that basically well-known phase field formulations that are completely computationally intractable unless it will give you results that depend upon this thing, unless you choose that interface thickness to be really the real interface thickness to be 1 nanometer, 10 nanometers. You get effects that are artifacts of this unrealistically thick interface. And so the takeaway message is that it's very easy to produce pictures. It's very hard to do something quantitative. You have to be much more aware of these effects according to delta. Okay, questions? Comments? So this is kind of an important issue, and we'll come back to that. We'll illustrate that in the lesson probably tomorrow about how you make the connection between reality and a phase field model. Okay, yeah. Oh, adaptive meshes can help a lot. Right. And so adaptive meshes can help. But even then, if you have a factor of 1,000 refinement in your grid, that can be pretty tough, actually. So it definitely helps. No questions. No questions. See, I mean, it's just an interesting question. I mean, so Bob Zakirka has this wonderful line that if the entire community had started with phase field models, we would have been overjoyed of the fact that we have this sharp interface model that we can write down that's independent of the interface thickness. Wow, a result that's independent of the interface thickness. We don't have to worry about resolving it. What a great model, right? And so the challenge is making sure that these two things yield the right answers. And to a certain extent, the sharp interface model is the right answer. That's what you're always kind of going towards. You know what the boundary conditions are. They're given by the Gibbs-Thompson equation, and you know precisely what you're doing. This is always an approximation to this in some way. And this is why when Jim Langer wrote down these phase field equations, there's this little note at the bottom of his notes that said, it's probably not a useful computational model because of this problem that I just illustrated here. And it turns out that's not entirely true, but you just have to be very careful. You just have to be careful. Comments? Okay. So everything I've done so far has been from conserved order parameters. And this is the Cahn-Hilliard equation. That's the Cahn-Hilliard equation. The other generic phase field model that you'll see, another equation that's used in phase field models are non-conserved order parameters, and it's and this is the Allen-Cahn equation. Allen-Cahn equation. So Cahn and Hilliard were at GE R&D, Research and Development Center, together in the 50s. Hilliard moved to Northwestern, Cahn moved to MIT, and Sam Allen was one of Cahn's PhD students at MIT. And they were interested in order-disorder transformations. And so John, coming from GE knew about gradient energy coefficients and diffuse interface theory, and he thought that this would be a neat thing to do to apply the diffuse interface theory to order-disorder transformations. From the standpoint of a phase field model, what people typically do is to use these equations, and they're sometimes often coupled together. So that's why we're treating them as independent parameters. But you'll see, if you look at solidification models and things like this, that we'll talk about a little bit towards the end of the course, these two things are always coupled. These are coupled together by free energy functions that depend upon order parameters here, for the order-disorder case, and composition for here. And they're coupled in a very specific kind of way. And I've kind of hinted at that with the Calpat free energy description I had before. So remember when we developed the Cahn-Hilliard equation, gradient of the generalized chemical potential, which you can write as the gradient of the functional derivative. And you'll see that notation used before. And then we said that the equation is conserved, which implies that you get the with respect to C. We're going to look at now at a case where the order parameter again called phi, is not conserved. Not conserved. And I gave you an example for this in an order-disorder case before. And I used eta for the order parameter there, but it's the same thing. And so the physics is very different because since the order parameter is not conserved, say you take something that looks like that double well free energy I gave you before. And if you started here, let's say 0.75, unlike the conserved case where it's going to break up into two phases, what happens if you start a system here, at this point it just rolls down the hill to this point down here. So it's non-conserved in that sense. And so it makes it, so you don't have to, so that means that you don't need this thing, right? And you don't need this thing really, because it's not a chemical potential. You don't have to worry about the chemical potentials. So the evolution equation is really simple. It's just moving down gradients in the free energy in order parameter space. So if you think about this equation over here, well, okay. And so we already know how to take that functional derivative. And it's just exactly the same thing we had before for the conserved case. So the only difference between the conserved case and the non-conserved case, basically in the Cahn-Hilliard equation that we've been working with, where m and k are not functions of composition, is basically the presence of a Laplacian. Where nothing's a function. So the Laplacian means conserved. If you don't have the Laplacian, it's non-conserved. And so let's look at this equation here. We can see whether I've written it correctly. So if you look at this point here, df d phi is negative. So this is less than 0. So that's negative. Negative times a negative is a positive, which means d phi dt is positive, which would move phi in that direction. They just roll downhill. So the only thing, that's why the minus sign is here, to make sure that you roll downhill rather than uphill. Okay. So you roll downhill to the bottoms of the wells. So that kind of makes sense. So say phi squared. The Euler-Lagrange equation basically is exactly the same as we did before, so we have the same results as before. before, that phi hyperbolic tangent of x over 2 delta, and phi, the interfacial energy, is a over k to the 1/2. Right? So it's the only thing, and why is that? Okay, let me step back here. So at equilibrium, another way to think about this is at equilibrium, that this thing has to be a constant, right? The gradient of a constant 0. At equilibrium, this thing here also has to be a constant or equal to 0 in this case. And that constant here is 0. That constant here can be a little different, but the results of the setting this thing equal to 0 gives you exactly what we had before when we set this thing equal to 0 to get the interfacial energy. Okay, so you get precisely the same interfacial energy. So what's different? What's different? The thing that's different between the two is the dynamics. So Guru was saying is that if you started with a sample like this, where you had domains of 0 and 1, and was periodic, what will happen is that you'll go to one domain with 1. If you apply boundary conditions such that at one place it's 1 and the other place it's 0, so you get an interface in this case, again, because of the boundary conditions that you apply, right? So what about the dynamics? And to illustrate this is let's repeat the linear stability calculation. Linear stability calculation of a uniform state. That is at equilibrium. And unlike the spinel decomposition case where you can have equilibrium if the composition's uniform, the chemical potential's uniform, here the equilibrium states are phi equals 0, 1, and 1/2. And so we do the same thing we did before. So you take a of x and t, so you take a small perturbation, and you get, so the equation we're looking at is phi same equation we had before, right? And now we're writing it in one dimension. So again, we have the same problem we had before, is that this is a linear term. This is nonlinear. It's pretty clearly nonlinear. If you look at this energy surface, it's nonlinear. And so when we write the perturbation here, the objective is to linearize or take care of that nonlinear term. And so d phi dx becomes t. The squared, the Laplacian goes to, like we had before, but now we have to Taylor expand the first term. Phi 0 plus the partial squared f with respect to phi squared 0, which is equal to partial f with respect to phi so remember, so we're starting the calculation from a uniform state. And if you look at the uniform states have the derivative of f with respect to phi equals to 0. So this term is equal to 0. And so that means that the partial of f to order epsilon is just this term here. So you put this first derivative term here into here. these terms into here. You can see that the epsilons will again disappear as we had before. You'll end up with a linear partial differential equation. You'll end up with an equation that looks like right? That's right. And so you take the Fourier transform of this. Fourier transform exactly as you did before, and you have phi, and phi is a function of you integrate it up exactly as you did before. So we can define the amplification factor as minus m k squared. And so you can look at the amplification factor as a function of k, just like we did before. Okay. If you look at the case where you're at the bottom of the well, so if you're at the bottom of the well, if you're down here, the curvature is positive. And if you're at the bottom of the well, that's positive, and you get something that looks like this. This is phi is equal to 0 and 1. Basically, it says that the equilibrium phases of phi equals 0 to 1 are stable. If you're at the top of the well, it's less than 0. That means that a minus times a minus gives you a positive, and you have a dispersion curve that looks like this. You have a critical wave number Kc again, but the and you have a damping of large wave numbers, just like what you'd expect. But for k less than k sub c, the dispersion curve looks like this. And so the wave number of the fluctuation with the maximum growth rate is q equals 0, unlike the Cahn-Hilliard case. Okay, and that's because this is a non-conserved system. In the Cahn-Hilliard case, in the Cahn-Hilliard case, you have to transport mass from one side to another in order to get this thing to work. So as the wavelength gets very big, that becomes a very long and difficult thing to do. It takes time. So the amplification rate of those waves as they go very, very long gets small. Here, you just start off with a system of phi, and you can immediately change phi equals 1/2 to 1 by just doing it uniformly, just moving it up, right? And so you get the maximum amplification at q equals 0, because you can just move this whole system like that because it's non-conserved, okay? And so the dynamics of the system are quite different, and we'll see the ramifications of this when we come to doing the phase field models. Okay. Questions? This one here, this last bit here, this. Yeah. So please ask questions. You know, so that for the alloys folks in the audience, remember we have in the back of our mind that this is an order-disorder transformation where we have these AB atoms, and so you can change from you can change the order parameter by just swapping one atom from one sublattice to another. Or if you're doing a magnetic problem, and this is maybe easier, you can change the phi equals 1 to phi equals in our case 0 by just taking the spins and changing them. And so you want to think about this case over here is that you start off with a system that's completely disordered. Let's say phi is equal to a half, and then all of the A atoms just kind of go to one particular lattice. They can do that almost instantaneously. In reality, that doesn't happen because of boundary condition effects again. So you start off with a fluctuation that basically says, well, you can start off with a fluctuation that puts you, some regions of the fluctuation put you over here, some regions of the fluctuation put you over here, and you go down from one region to the other, and you do end up with a phi equals 1 and phi equals 0, right? But in this linear stability context, this is the maximum growth rate. And so if you started, so you start with a system like right here, and you take a small fluctuation. And so if one of the fluctuations has a value of the order parameter that's less than a half, it's going to roll down here. If it ends up with a fluctuation that's greater than a half, it's going to roll down here. And so what you end up with is a case that looks like this, where you have 1 on one side, 1 on the minus in the other, and this is called an antiphase domain boundary in the composition case. And it's the antiphase domain boundary because you have a lattice where you have in 2 dimensions it looks like this. And then you come up to the antiphase domain boundary. In this case, it's infinitely sharp, and it looks like this. And so in this region here, you have eta equals 1 over here, phi equals 1, and phi equals 0 over there. And so you can have this antiphase. So over here, it involves energy because the system likes to have these A and B atoms kind of together like this. And over here, you can see that these atoms are kind of not in the same arrangement. So there's an energy associated with this. And that's the antiphase domain boundary energy, which is what we calculated essentially here. Okay? So yeah, even though this has the maximum growth rate, it has, in many cases, the initial condition can be such that you wouldn't get that if you separate from both sides. Yeah?
What determines the functional form that we get?
For this,
We are using
yeah. Yeah, in fact, in most cases it's not, in many cases it's not that. The nice thing about phi squared 1 minus phi squared is that you can actually get analytical solutions. And so if you remember the free energy, the CalFat free energy example I gave where you have to extend the free energies in a third dimension, composition and order parameter. A lot of them are built upon these kind of free energy functions for the order parameters because you can integrate it easily. You can understand what's going on. In many cases, for example, when you're using CalFat free energy functions or things like that, it gets more complicated, and you can't do these integrations analytically. It depends upon the free energy functions that you want to use. So it's actually a very good question because the idea is that you can calculate these free energy, the interfacial energies, and you can calculate the interface thicknesses, and you kind of know what the scalings are. Kind of go back to this simple Landau expansion of the free energy, which is not rigorous except near critical points. Really. Yeah, that's right. That's right. Well, by construction, we're all only kind of going between 0 and 1, right? And one of the problems with some phase field models is that you're supposed to be between 0 and 1, and you integrate in time, and you eventually start getting things that are greater than 1 or less than 0, and bad things can happen. So it's by construction that we only go from 0 to 1. Basically only go over this energy barrier, that's another good question too. Because I want to emphasize that, because if you look at the real free energies in the system, the real free energies look like this. And over here, the slopes go to infinity. And so it's impossible to get an order parameter less than 0 or greater than 1. Whereas here, it's kind of like a Taylor expansion, it's a Landau expansion. So it's kind of, sometimes you can leak out over the other sides. And the reason why people don't use these models, these regular solution type models, is that it's x log x, right? So you have this complicated thing you integrate. You can't do it analytically, and it's hard to figure out. So on Monday, we'll talk about grain growth. And I'll derive the Allen-Kahn equations for grain growth. I'll do the asymptotics, and then I'll put together a multi-order parameter model for grain growth, and I'll show you how strange things can get when you do that, if you don't choose these free energies right. Yeah.
One more thing that you can point out is that both the equations, Kahn-Hilliard and Allen-Kahn, look like diffusion equations. There is a del squared.
That's right.
And then there is a nonlinearity which is in the function form here and which is in the del power 4 in Kahn here.
Yeah. Yeah. So
this is a reaction diffusion.
that's right. That's right. So if you want to think about this, let's look at the Allen-Kahn equation. That's it. So let's expand on that a little bit. I think that's a good point. So if the Allen-Kahn equation looks like, right? If I have the signs right, I don't know. Geez, I've had problems with signs. Okay, I got the signs right. Okay, so so that looks like a diffusion equation, and then you have a source term on the other side, and that's what Guru was saying, is that it's basically like a reaction diffusion equation where you have a forcing term that's nonlinear plus something that looks like a diffusion equation. So one of the nice things about the Allen-Kahn equation is that it's very easy. It's easier to solve numerically, as you'll see this afternoon, than the Kahn-Hilliard equation, and that's because the Kahn-Hilliard equation has fourth-order derivatives. And since the fourth-order derivatives, the equations are that much stiffer. The Allen-Kahn equation only has second-order derivatives, and so it kind of looks like a diffusion equation. It's easier to solve. It's easier to solve numerically. Yeah. So if you had, let's say, a nickel aluminum is an example that I know because it's been parameterized a lot. And you start off with a nickel atom here, and you can compute the interaction of a nickel atom and an aluminum atom. Oops, sorry, it's aluminum atom, a different species. There's clearly going to be an interaction, right? But as you put more nickel atoms around this aluminum atom, you put another aluminum atom out here. The question is, does this aluminum atom and that nickel atom see each other? And that's the interaction range I'm talking about. And in fact, in nickel aluminum, you could be fifth order nearest neighbors, actually. It's fairly long ranged. And so this aluminum atom knows that this nickel atom exists, even though it's not in its nearest neighbor shell. And that's the interaction distance I talked about. And so the reason why you see the linear theory of spinel decomposition of polymers is because this interaction distance is on the scale of the chains, which is very, very big. It's very mean field-like. Whereas in atomistic systems, like an Ising model, where you only have nearest neighbor interactions, then the interaction range is very short. If the interaction range is very short, this whole idea of gradient energy coefficients you can kind of question, which is why people think you don't see linear spinel decomposition in a metal. So there was a fellow who's at Argonne, by the name of Brian Stevenson. He was an X-ray synchrotron person, and he worked very hard to do ultra-fast quenches into spinel regions to see if you could measure the structure function or the composition fluctuations to see if the linear theory holds. And he did millisecond quenches, and he still didn't see the linear theory. So even though the composition fluctuations were extremely small, you were almost uniform, and he worked very hard to worry about vacancy concentrations. I mean, it was a very hard experiment. He still didn't see the linear theory. Kind of an interesting question. So when I asked John Kahn about this, And his response was that in a crystal, every time you have a composition fluctuation, you generate long-range elastic stresses, and we'll talk about this in a couple days. And these long-range elastic stresses give you longer-range interactions, which mean that you should see the linear theory, for at least in crystals with systems that have long-range elastic interactions. It's a good PhD thesis for people. Still an unknown, unknown question out in the literature. Other questions? You get a chance to choose, prove John Kahn right.
Okay, there are no more questions.
Okay.
We have two more people joining us.
Yes.
So, welcome them. And we will have lunch now. And we come back at 2:30 and start the program.
Okay, thank you very much.